3 first.
The first thing is just write out the Lewis structure for GS3.
So we can do that, yeah.
Write out the Lewis structure. Boron has how many valence electrons? 3. And then we have 3 fluorines. Each fluorine has 7 electrons, so 24 electrons altogether. And then most likely we'll throw boron and then attach what to it? Just the fluorine. We get something like this. Then we complete the octets. So each fluorine will need an additional 6 electrons, plus the 2 from the bonding will give it 8. And then boron has how many now surrounding it? 2, 4, 6, so it's going to need an additional 2 electrons to complete its octet. And so now everybody has an octet. You look at that, and then what do we do next? What's the next step? No? Not the next step. Okay, what is the next step? So we just completed the end of step 3, add unpaired pairs. So we just add what we call lone pairs to complete the octet around all atoms except hydrogen. The next step is to do what? Yeah, we're going to count the electrons in the structure and compare it to the electrons here. So we're going to make sure the electrons match. So how many electrons do we use up here? So this 2, 4, 6, 8 times 3 is 24 plus 2 is 6. So we use 26 electrons, which is too many electrons. We can't. The electrons have to match. And so what do we need to do to get them to match? Well, we got to remove. We have to remove 2 electrons. We got 26. We need to remove 2 to get to 24. So who are we going to take them from? That's why this sentence is not good. If the diagram has more, then we have to remove the lone pair from the least electronegative atom and try to form a double bond with an additional lone pair. So the diagram has more. We're going to remove 2 from the least electronegative, which would be what? Which would be boron. And then we'll try to form a double bond with another lone pair. So that means we'll take a lone pair off fluorine. Okay, we'll take this one and then make a double bond like that. Okay, now you look at this and how does it look? It looks good because everything has an octet. Right? But we need a step 6 here. There's no step 6. Step 6 is to do what? Well, we got the total of 4 electron pairs. 4 electron pairs pairs is an octet, 8 electrons. And so we make sure that, I would rewrite this too. I don't like how it's written. I would just say, we just check to make sure everything is an octet except hydrogen only needs a duet. And then step 6 would be what? Formal charge. We've got to look at the formal charge. Okay, so tell me the formal charges here. What's the formal charge on fluorine? 0. That's correct. This fluorine's 0. This fluorine? 0. This boron? Boron normally has 3. Carbon's 4 valence electrons. Hydrogen's 1. Nitrogen is 5. Oxygen is 6. Fluorine is 7. So boron is what? Minus. And this fluorine up here? Plus. And so how would you verbally state what happened? Well, verbally stating what happened is boron took an electron from fluorine. Because boron ends up with a minus charge, fluorine ends up with a positive charge. Is boron strong enough to do that? You think boron's strong enough to take an electron from fluorine? No. No. I mean, boron's electronegativity is 2.0, fluorine is 4.0. Sometimes it does happen that it's very rare. The only way, sometimes it does happen where, but they got to be a bit closer in terms of electronegativity. This is a pretty big difference in electronegativity. And so there's no way that fluorine's going to give up, because when it creates a double bond, it still has an octet, but it's giving up electron density because it's going to share a pair rather than have the pair entirely to itself. So that sharing is giving up some electron density. And so in this case, is fluorine willing to give up that electron density? It turns out, no, this doesn't happen. Fluorine, this is another rule. Fluorine only forms single bonds. Single bonds. That's it. And so what we end up with is this situation where boron is just going to have to suffer with less than an octet. And so at the end of this chapter, chapter 12, we see here that there are going to be exceptions to the octet rule. One of the exceptions is BF3. Why? Boron's not going to have an octet. Why? Because fluorine's not going to give it an electron. It's not strong enough. Same thing with beryllium. This is beryllium difluoride, which is a molecular compound. Normally we think of metal and non-metals being ionic lattice. This turns out to be a molecular compound. Beryllium is not going to have an octet either. It requires this fluorine to give up a pair, and this fluorine to give up a pair. It's not going to do that. That just happens with fluorine. Fluorine is not going to form multiple bonds. That's all there is. Now, sometimes the formal charge is a little weird. Sometimes the formal charge is a little weird. there's always this thing, you know, what should you do with the formal charge? Well, while we're on this topic, let's look at oxygen. When we do oxygen, which is O2, what would the Lewis structure for this be? The Lewis structure is going to look like this. You know, if we do it like this, you know, one of the oxygens will have an octet, the other won't. And so if we take this pair and bring it in here, we can form something like this, where the oxygen will double bond like that. This would be the Lewis structure. It says it is impossible to write a single Lewis diagram that satisfactorily explains all the properties of molecular oxygen. That's because Lewis structures are based on, look at these structures. The advantage of Lewis structures is that they're not terribly difficult to generate. The disadvantage is they're a simplification of the full quantum mechanics of this. So what this statement is saying here, oxygen, is we have to use the full quantum mechanics to really explain the properties of oxygen. And so, Lewis structures is based on simplified quantum mechanics. So we might say it's the quantum mechanics light version. You know, the light version doesn't have all the fancy features of quantum mechanics, but it's easier to use. For oxygen, we need the full version of quantum mechanics. The full version we call molecular orbital theory here. Which we aren't going to get into in this class. And so this is the Lewis structure for O2. This is the Lewis structure we generate for O2. In fact, let's take a look at Wikipedia and see what Wikipedia has for O2. This is what we call molecular orbital theory here. You can see this diagram here. This is a molecular orbital energy level diagram. This is the best way to describe an oxygen molecule. The electrons occupying these things called molecular orbitals. Maybe they don't even talk about the Lewis structure. Like Wikipedia has it. Most people, when they try to visualize an O2 molecule, they see something like this. Oxygen, oxygen, double bond with two lone pairs on each oxygen. Like this. Well, images. Fluorine is not going to give up its electron density, but oxygen might. So let me talk about carbon monoxide next. Let's draw out the Lewis structure for carbon monoxide. Why don't you try that?